Welcome to this module on estimation and SEM. In today's lecture, we're going to talk about how M+ actually finds and derives estimates for parameters. This is important so that you understand where these values are coming from and also how to navigate and resolve issues that may pop up when you have issues with estimation. So to start with, I want to go back to what we were talking about in the last module when we were talking about identification and specification. So if you remember, in M+, when we were actually proposing a model, what we were doing is proposing a series of structural equations. And when we have an under-identified model, this is what's on the right side of this slide here, we can have a variety of equations that don't have a single exact answer that can be estimated for a single parameter. So in this example here on the right, you have A and B are the two parameters that we are doing, where 6, 10, and 12 are the three observations. So those would be equivalents to like a covariances in our covariance structure. So what we have here is we can't get an exact parameter for A and B that works for all three. So rather what we could do is find a value for A and for B that has the smallest error. So the smallest difference between the possible answers. Essentially, M+ is doing the same thing with estimation. It's finding the possible parameter estimates that could resolve or could be an answer for all of the series of structural equations that you have proposed in your model, and then finding the smallest difference between them. So in order to talk about this and understand this at a little bit more deeper level, essentially we're going to go down the rabbit hole a little further here. So we're going to talk about the covariance, reproduced covariance, and residual matrix. So these are three different kinds of covariance matrices that kind of get developed when we are doing a structural equation model. So covariance matrix is just your simple covariance matrix to your sample. So remember, a covariance is just an unstandardized correlation. So if we actually ran a correlation table or developed a covariance table straight from the data, this is the covariance matrix. The reproduced covariance matrix is the covariance matrix for the model that you are proposing. And when you have an under-identified model, there's going to be a difference between the covariance and reproduced covariance matrix, just like we see on the right side of this slide. Now, in fact, there's going to be a little bit of a difference. The residual matrix is the difference between the covariance and reproduced covariance matrices. So when we have an under-identified model, we're going to have some residual left over. There's going to be some difference. When we have a just identified model, it's going to be zero. There's going to be no difference. So this is what that looks like here. If you look at this as an example of a covariance matrix, reproduced covariance matrix, and then the residual covariance matrix. And the idea is to get that residual covariance matrix as close to zero as possible. So when M+ is running parameter estimates and trying to determine what the best parameter is for each of those parameters in your model, it is trying to get that residual covariance matrix as close to zero as possible. To kind of summarize and review, the problem with parameter estimation is that it is impossible to reproduce exactly the sample covariance matrix, which is going to result in some error in our model. Now, M+ wants to measure that error and also get that error as close to zero as possible. But what this brings up is really two important questions. First, how do we determine the residual matrix? How do we determine how close to zero does it need to get? And then also, how do we actually go about estimating the parameters from that covariance matrix? So the answer to these lie in our estimation method. There are a variety of methods that a variety of programs use. Maximum likelihood estimation, or ML, is the one that is most commonly used. So it's not used only to evaluate or adjust for missing values, but it is also used around the actual estimation for parameters. So maximum likelihood, or ML, estimation. A little bit about that. One, it's the most widely used. While there are other estimations out there, and the readings you'll do this week will talk about a few of the other kinds of estimations that are out there. Um, but ML is the one we're going to talk about because that's the one most commonly used, and it's the one that I would have you use for this class. And there's a few reasons for that. One, ML for just identified models. So remember, that's when we have perfect model fit. There's no difference, no degrees of freedom. Any difference between multiple regression and ML are essentially zero. They're the same. And then when we have an over-identified model and a recursive model, that we find that there is some difference, but multiple regression and ML are pretty close, especially when you have large sample sizes. I just realized, little caution here, in the past couple slides I said under-identified when I meant to say over-identified. So please note that correction, that in the past couple of slides I may have said under-identified when I meant to say over-identified. A few other important pieces about ML. So ML, what it essentially does is it estimates the maximum likelihood that the data were drawn from the same population. So when it's trying to determine the best parameter estimates, and it's using, we have an over-identified model, so we have positive degrees of freedom, that it's trying to determine that the maximum likelihood that those estimates are accurate. ML assumes normal theory, and what that means is it assumes normal data and a few other things. I'm going to talk pretty explicitly at the very end of our slides here about the assumptions for ML, but it assumes a normally distributed variables. So all that stuff we talked about running your preliminary analyses and making sure you have adequate correlations and making sure that you have meet the requirements for normality are really important for ML. If you violate normality, there is a more robust version of ML. It's MLR, so it's ML robust. But if you use that, it does do a lot of the estimations differently. And when you get into model comparison and comparing model fits, which we're going to be doing a lot of, it becomes much more complicated. So if you need to use MLR, make sure you come and talk to me so we can kind of go over how to do that. And something else that we've seen, this is the last point on the slide here, is that because ML is such a commonly used estimation method, and it has become really the estimation method of choice and preference because of its reliance on normal theory and because of how well it's been documented to really provide really good estimation, that if you decide to use something differently, such as MLR, you do need to explicitly justify why you are using a different estimation method than ML when you write up your results. Okay, so the next things we're going to talk about is a little bit about how ML actually works and how you can make some adjustments in your syntax when you're having some problems with estimation. So ML, when it runs, the whole full information likelihood piece is that it's actually estimating everything simultaneously. Everything's getting calculated together all at once. All of those multiple equations in your that you are asking the program to run with your model are all being done at once. This is called a full information method. When you're running hierarchical regressions in SPSS, when you're doing multiple regression in SPSS, it is a partial information or a limited information method. And what it does here is it just analyzes basically like one at a time. So in SPSS, it's essentially doing one at a time or a few little groupings here and there, versus in M+, with ML, it's doing everything at once. So it's full information. We're getting all the information together at once. Another piece about ML is that it is an iterative process. So iterative means doing it again and again and again. Like writing is an iterative process. You're going to be going back and forth and changing things and going back and doing things over and over again. So when ML runs, it determines a starting value, and then for each parameter, and then it's going to go back and redo it through subsequent iterations over and over and over again, trying to improve those estimates. So improvement means the overall fit of the model to the data generally becomes better from step to step. So it's trying to develop parameter estimates that make that model fit better and that residual covariance matrix smaller. And it will do that over and over and over again until you reach convergence. So convergence is the level where you have defined this is the place where you can stop. You've found enough error, or you've had a low enough error that we're comfortable here when you're doing this. And then when you have run your model and it goes through those iterative processes over and over again and it reaches convergence, so it gets that error to be small enough that we're comfortable with it, then you'll get this wonderful message in your output that says the model estimation terminated normally. That means it reached convergence. So in the analysis command, that's where you determine like the type of analysis you're doing. You have the estimator, iterations, convergence. Now in past slides, I've told you never touch these. And generally, you're never going to mess with these. But this is for you to understand where this is. And if you do need to adjust any of these, you know how to do that. So you'll see here that under the analysis command, this is the syntax you would see in M+. You have type is normal or type is missing, semicolon. Estimator is ML. That's determining what kind of estimator you're using. If you're going to use the more robust version, you'd say estimator is MLR. Or if you're going to use a different kind of estimator, you'd say estimator is, and then state the estimator. But 99% of the time, you're going to be sticking with estimator is ML. The iterations, now that is how many iterations it's going to do until it stops. So when we say iterations is or iterations equals 1,000, that means M+, go ahead and do 1,000 iterations. Try to reach convergence 1,000 times. If it gets to 1,000 and it has not converged, then it will stop and say, I wasn't able to determine or to terminate the model, and you'll get an error message that it failed. Convergence is that level that we talked about. So convergence is or convergence equals 0.0005. That is the level of error or residual that we are comfortable with. Typically, you are never ever going to change the convergence level. You can if you have an issue where the model did not terminate normally. The first thing you can do is actually increase those iterations. So you can go from 1,000 to 2,000. Maybe it just needs to keep going a little bit longer for it to reach convergence and terminate normally. So if you ever change anything in here in this command, you would be changing the estimator or the iterations. The convergence you will probably typically never change. If you do, especially if you make that convergence larger, you can really have some real problems in your data because it won't be very accurate. So again, if convergence does fail, it's important to not reduce or make that convergence rate smaller just to make it fit. But you can sometimes increase the number of iterations. That can sometimes fix the problem for you. Now, when there are problems with convergence, oftentimes that's around model specification, poor start values. The model is too complex for the sample size that you have. We're going to go into detail, pretty good detail here about issues with convergence and issues with the modern, with estimation. But first, I want to talk about the assumptions for maximum likelihood estimation. So assumptions for ML. Most of these assumptions should look pretty familiar because there are things that we've talked about in either multivariate, the multivariate class, or we've talked about earlier in the semester. So ML assumes independence of observations, so independence that we have had as an assumption since the beginning of covering multivariate statistics. It assumes multivariate normality of the endogenous variables, so we want to make sure that our variables are normally distributed. Independence of exogenous variables and disturbances. So that's all that stuff we talked about with specification, making sure that we aren't creating correlations across exogenous variables and endogenous variables, or correlating disturbance terms where we create bow patterns. Exogenous variables are measured without error, and correct specification of the model. So essentially what we're assuming with ML is that we've specified and identified our model correctly, and we have multivariate normality. If you violate those assumptions, especially that assumption of normality, we can get we can get a lot of errors in our parameter estimates. So specifically, a lot of researchers found that the value of the parameter estimate may be accurate in large samples, but the standard errors will be really underestimated, sometimes 25 to 50% too low. And when you've done that, essentially what you're doing is inflating your type 1 error. As that as the residuals are underestimated, then the fact that you're going to accept that model is going to be much higher. And so what's going to end up happening is you're going to be rejecting the null hypothesis falsely. You're going to be saying this model is correct, when in fact the error in the model has been vastly underestimated, leading it to look much better than it actually is. The values of test model statistics tend to be too high. So again, we're increasing that type 1 error. When we violate normality, when we're using ML, we're going to be much more likely to have our model look much better than it actually is, and end up accepting that model when in fact it may not be accurate or actually relevant to what reality is. So if normality is violating, you should really be using that robust version. So that's, I think in the past I said MLR, it's MLE. So I said that wrong before, but MLE is what you'll actually do. So this creates more robust standard errors and changes some things around the goodness of fit to make sure that it's accounting for the non-normality in the data. So a few important aspects of ML that I've hoped that I've really hit home now is that specification is so important. If you have not specified your model accurately, then in these estimation methods that we're using like ML, errors tend to propagate throughout the model. So errors get worse and worse and worse throughout your model when you have violated the assumptions of ML. So specification is really important, and making sure that you've done your preliminary analyses to assure yourself that you don't have issues with normality or multicollinearity or other kinds of common assumptions that we have. So in summary, the more problems that we have with specification error, the more error we're going to have in our model, and this can really result in a really biased model that is inaccurate. So really important to make sure that you're specifying your model correctly, and also that you're doing your preliminary analyses to making sure that you meet the assumptions of normality. So now I want to talk about some common problems with estimation, such as Haywood cases and non-positive definite and bad star values, and how to go around correcting some of these issues, essentially troubleshooting problems with estimation. So one of the most common issues that you may have is a Haywood case. A Haywood case is basically an illogical or what should be an impossible value for a parameter estimate, like having a negative variance. It shouldn't be possible that variance is negative because you're taking the square root of things when you are getting your variance. Having correlations outside of -1 to 1, or having error variance that is way, way too big, especially in comparison to the other error variances. So when you have a Haywood case, or when you have problems with positive definiteness, you will commonly get an error, and it will usually first say the model terminated normally, and then it will say warning. There will be a warning under that, and it will be in all caps, and it will say something like the standard errors of the model parameter estimates may not be trustworthy for some parameters due to a non-positive definite first-order derivative product matrix. So that sounds really complicated, but what it's essentially saying is you had an issue with estimation. It may further in this warning error tell you exactly where that parameter, the issue with what parameter may be, and it may not. But it will tell you that like modification indices couldn't be computed. That's another common thing it may get, so you won't have any model fit indices. And it will tell you the model may not be identified, or it may tell you that don't trust the results. It looks like there's a real problem here. So M+ will try to tell you when it has run the model and given it or gotten results, and it sees some things that shouldn't be possible, or sees some real problems in the results, and it's going to warn you, don't trust this, or warn you that I couldn't do this. And so this is where there's been an issue with estimation. So I'm going to go through common issues and then common troubleshooting. So some common causes of model estimation errors. Specification errors are usually the first common problem where you have not specified your model correctly, or you have too few parameters or too many parameters based on the number of the sample size that you have. You can have an under-identified model, so that's where you have the negative degrees of freedom. And then you have an identification issue. The sample size can be too small for the model being tested, so your model is severely underpowered. Your model is too complex for the sample size. You can have outliers in the data, so again, you haven't adequately done your preliminary analyses, getting rid of and or accounting for outliers in the data accurately. You can have a problem with non-convergence, where you need to increase those numbers of iterations. You can have correlations that are too high or too low, so there's not enough adequately correlated values to do anything with, or you have issues with multicollinearity. You can have bad start values, so that place where it starts, its first iteration, can be a bad starting place. You can have too much missing data, so ML typically can't handle more than 20% missingness. Violations of the assumptions of ML, so violations of normality. Having two indicator-linked variables can cause a lot of problems. As you saw in your readings from last week, that when you're doing a two indicator-linked variable, that there's a lot of rules to follow with that. And so making sure that if you have a two indicator-linked variable, that you're following all the rules for that. You can also have this issue of empirical under-identification. So this is an issue where you do have an over-identified model, so you have positive degrees of freedom, but it's empirically under-identified. So there isn't enough information in the covariance matrix to compute or valid parameter estimates. So what do you do if you have issues with estimation? First thing, check your specification. So that means check your model, check your syntax. Very commonly, I found that when I have an error of this kind, I'm missing a semicolon on one of my model commands. Checking that you've actually scaled your latent variables, and again, we're going to get to that when we cover CFA in a few weeks. Check for bow patterns or non-recursive models. Check the CFA, make sure that you have factor loadings that are each at least 0.4 or higher. And again, that's going to make more sense when we get to CFA here in a few weeks. Secondly, check your model power. So this is back way at the beginning of the semester, page 16 of the Klein book. It talks about the NQ rule. So this is the ratio of participants to parameters, where N is the number of participants and Q is the number of parameters. You now know how to calculate how many parameters you have in your model. So you can go back and calculate your number of parameters and look at your sample size. You should have at least 20 participants per parameter. So if your model is really underpowered, you don't have enough participants per parameter, that can cause an issue with estimation. Next, check on data issues. So check those outliers. Check variances. So go back and run some preliminary statistics. Outliers and variance can also cause a real big problem. So when we have variances that are extremely high or extremely low in comparison to other variances in the model, that can be a problem. So check your variances, check for outliers. Also a very common issue that can happen is that when you have changed your file and gotten it ready for M+, when you've made that .dat file and removed the variable names, you've actually made some errors in your syntax in M+, where, or in transferring it, where you have not adequately said this variable equals this column of data. So it can be helpful to open that text file and count up your number of columns and making sure that that matches and that they're in the correct order, that you're calling the variables the correct names in your M+ syntax. And lastly, a few other common data issues are having categorical variables that you have not adequately told M+ that they are categorical variables, and violations of assumptions. So where you first want to start is specification, model power, and data issues. 95 out of 100 times, going through these troubleshooting pieces here, you're going to fix the problem with estimation. And the vast majority of time, the issue is with syntax missing semicolons or not converting your data correctly over to the M plus. And then underpowered kind of come after that, as well as outliers, variance issues next to that. The last troubleshooting piece that you want to cover is bad start values. So as I said before, start values is that initial value where M plus is starting. You can actually change that start value. If you choose to do that, the best place to determine the starting value is actually just to run a simple linear regression in SPSS with all the variables in there. And just figure out the best, and using the regression weights, the beta value, as the starting place. So using that unstandardized beta value as the starting place. The syntax for doing this is pretty complicated, so I'm not going to give that here. And it's pretty rare that you'll have to change a start value. I've never had to do that before, and I know, talking to other researchers, that this is really, really rare where you have to actually change your start value. So if you have to deal with this, come and talk to me and we'll work through it together. But doing the other troubleshooting issues on the last slide should be able to fix any problems with estimation in your model. In our next module, we're going to get to running models in M+. And we're going to have two sets of lectures. The first lecture is going to be on model fit. So it's going to be all about how to interpret model fit in your output. And then we'll talk about how to interpret results, how to actually read the results in M+, and interpret those and report them in journals.